order. Well, here, having a power of 2, you have the subgroups are all in a chain, you know, from the biggest one to the smallest one. So the so-called lattice of, sorry, I'm borrowing this word, the lattice of subgroup is very simple. It's just a chain, okay? And each of the subgroup is defined by this property that you take the elements such that when you raise it to the 2 to the I power, you get 1. This uniquely defines a subgroup with 2 to the I elements. And then there is another property that whenever you take an element here, then when you raise it to this power, either you get 1 or you get the generator to the 2 to the n minus 1. So there are these two possibilities always. And this is actually quite simple to check, because if you take an element like this, well, if you get 1, fine. If you don't get 1 and you raise it squared, well, if you raise it squared, then you have a to the power of 2n. So a to the order of the group. So if you have an element and you raise it to the order of the group, you always get 1. Right? This is basic group theory. So if you take an element, you raise it to the order of the group, you always get 1. Okay? So if you take this element and you take the power of the order of the group over 2, then there are two possibilities. Either you get 1 or you get an element which squared is 1. And there is only one element which squared gives 1, which is the proper power of the generator. And these are the only two possibilities. So I'm not saying here that A is equal to G, right? This is not quite what I mean. What I mean is just when we raise them to this power, we get the same element. Okay? And this is a simple fact of finite cyclic groups. And then from this observation, we deduce this algorithm. So I'd like to discuss this algorithm with a fair amount of details also. So here's the situation. G is cyclic, and the order of this group, I like to write the order in many different ways. Okay, you bear with me, right? So this is a power of 2. This is the situation. And then I'm given myself, as usual, I want to say in the same notation, I want to solve A equal G to the K. So K is what I want, the discrete log. Right? Well, what I know about this K is that this K is going to be an element of Z mod order of GZ, right? So in particular, K is strictly less than 2 to the power of n, right? And bigger or equal than 0. So this K will have a binary expansion. So K can be written as K0 plus 2K1 plus dot 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 plus 2 to the n minus 1 times K n minus 1, right? Where this K i's are zeros or ones. So this discrete log, which I want to compute, will have a binary expansion, right? Like every number. And by construction, it has to be, since the element is less than 2 to the n, the number of its binary digits, the size of this number is n, right? because it has m binary digits. So what we need to compute all these zeros and ones, right? So let's